My dear students, other viewers and listeners, I, Professor Manohar Lal, School of Computer and Information Sciences, IGNOU, invite you to this lecture on Theory of Computations, which is also a syllabus, a course in the BCA program of Indira Gandhi National Open University. Friends, generally, not only in this university, but almost all over the world, the significance of this subject, theory of computer science, is not generally taken as it should be. The subject is very important, however, the attention generally the students give to this discipline is very little. They think that it is almost an irrelevant and to some extent even useless discipline. However, whatever I am going to say, through that I like to impress upon you that theory of computation forms one of the most important subjects of any program in computer science. In this lecture, I'll give an overview, under which I'll also highlight the significance of the discipline. Friends, as in my lecture later on I'll tell you, it is actually the theory which preceded all the practical applications by at least 1 decade. This is a strange phenomena. Generally in all other scientific disciplines, it happens, first of all there is a phenomena, it is practiced, and out of the practice some general principles, and ultimately some theory comes out. However, in the case of theory of computer science, the theory of computer science, most of it preceded the practice of computer science. In this respect, in order to justify whatever I have claimed just now, I like to have a look at the historical development, various developments in computer science which took place in historical order. So friends, most of the developments which may be said to be of theory of computer science started taking place around 1930. Though those developments were not in vacuum at all, those were the developments which were a consequence of a number of crises in mathematics, and the mathematicians found that their foundations are weak, and in the search of the sound foundations for mathematics, the output, unintended output, was theory of computer science. So please, I draw your attention to some of the historical developments in computer science starting with 1930s. Please look at the slides. In the 1930s, the fundamental concepts of computing were developed by Gödel, Turing, Post, Church and others. Friends, this was really a fermenting year where a lot of development, theoretical developments took place. I'll go into the details how those theoretical developments took place, but here just in order to connect the theory of computer science, the developments in theory of computer science which took before the actual computer science practices, I want to relate those to the rest of the developments. Therefore, here just I want to tell you that the most of the theoretical developments in computer science took during the 1930s, you can say from 1930 to almost 1940 or so. In the 1940s, we had the practical, some computer systems with their hardware were implemented by some of the leading lights of that time. For example, Neumann, Eckert and Atansov, along with a number of other dignitaries or well-known persons, actually implemented a computer system. So this was the period when we had the actual hardware computer system. Before that, we only had the other calculating machines, but the type of computer which we take as computer today, in the sense which has memory, which have execution units, etc., etc., that was designed and developed during the 1940s. And during the 1950s, once we had a computer at our disposal which worked on only voltages, binary voltages or binary other physical elements, was programmed to solve problems and for that purpose, higher level languages, particularly the Fortran, Lisp and COBOL were developed during the 1950s. Fortran was developed for the purpose of scientific applications, whereas Lisp was developed for the purpose of artificial intelligence applications, and COBOL was developed for the purpose of business applications. So these three languages were developed during the 1950s, that is the period covering from 1950 to 1960 almost. During the 1960s, please look at the slide. Rapid developments of the subjects like algorithms, data structure, databases, operating systems which form the core of computer science today. Any computer science program today must be discussing these as subjects like algorithms, data. So these developments took place during the 1960s, that is, you can say the period between 1960 and 1970. 1970 is the emergence of the software engineering, because as we went ahead with applications of computer in solving everyday problems, it became essential that more and more difficult problems may be solved, because the earlier problems when got solved, people aspired for next more difficult type of problems to be solved with the help of the computers, and therefore whatever the earlier subjects like data structures, operating systems, etc., were found to be wanting in solving the more complex problems, and therefore it led to the developments of software engineering, structured programming, object-oriented programming during the period from 1970 to 1980. During the 1980s, that is the period between 1980 and 1990, the emergence of personal computing and networks. Actually, the computer networks played a very important role in the development of applications of computer science, which placed the personal computer in the hands of a common man. Before this time, the computers were only in the research labs or big organizations. Even small organizations did not have much use. Of course, these were being used, but most of the time the computers were found only in the research labs of big universities or in the big organizations. So this was the period, you can say, a revolutionary period, in the sense that the computer was placed in the hand of a common man, and that popularized the use of computers in solving problems. So this is the period between 1980 afterwards. You can say between 1980 and 90, but after 1980 you can say many people started using computer apart from research organizations and big organizations. Then the 1990s is so close, most of the people know what are the developments that took place during this period. The period is characterized by explosive growth of the internet and the World Wide Web. Use of multimedia, also increasing use of... Now, by and by, when we started solving problems with the help of computers, you may not look at the slide, it became that the use of the computer system is very difficult. That is, of course it was very useful, but they found that using a computer by a common man was quite difficult. If a small spelling error or in the command or somewhere occurred, the person was not able to operate. So more attention started being devoted to this aspect also, how to facilitate the use of the computer by a common man. And this is the period, say, after 1990s, more and more attention was started being given to facilitating the use of computer. That is, the interaction with the computer was also became a major topic of research for computer scientists, so that it can facilitate the use of this one. And friends, nowadays you can see currently that we know the many scientific problems and other problems are amenable to solutions by computers. So next step is to other domains like social, legal and medical, ethical. These are the areas where it was found, why not the applications of computers be there to these disciplines also, because these disciplines are not very precise like the scientific disciplines. So this was the next Now, so friends, I have given you an overview of the developments in historical order, and in this order you see that the theoretical computer science preceded the practical computer science. Most of the development, most of the theory you can say was developed between 1930 and 1940. Now what is the essence of that, though we will be discussing in other slides also later on, but the essence of the research. But before I go into the research, essence of the research, I would like to give a brief historical view of how the developments during 1930 to 40 took place in theory of computer science without any computer having been developed by this time. Friends, in this respect I may tell you that actually in mathematics there were a number of problems which did not have satisfactory solution. It prompted the mathematicians to investigate further, particularly the problem of epsilon in the differential and calculus, which says that epsilon is greater than 0, it is any positive number smaller than any other number. Now it is a paradoxical or contradictory in itself, and it led to a number of problems, foundational problems. They started searching their foundations. That is, what are the problems in the fundamental problems in mathematics? And in the search they found out, one of the most important things which the mathematicians found was that the use of natural language is a disturbing factor. That is, a special language may be designed of symbols which have precise meaning, and that language should be used for doing a whole of mathematics, which led to the developments of, you can say, predicate and propositional calculus, etc., though these subjects were earlier also there. But the symbolic propositional calculus and symbolic predicate calculus, though symbolic may be redundant, but I am emphasizing that the symbolic aspect was emphasized, that whatever is said in terms of a finite number of symbols using well-defined functions and all that is essential in order that the ambiguities or the problems of mathematics are solved. And this formalization movement ultimately led to the fact that a system should be taken as formal if it can be implemented on a machine in which the human intervention may not be required. So a machine, though the computer came later on, but whatever can be implemented in one way, we can say a formal system, in only one way, I am saying, emphasizing, a system can be said to be formal if it can be executed, if can be understood, or if not understood, at least it can be implemented on a computer system. Now I come to what is the essence of the research during the 1930s and 40s. I come into the details, but in a few sentences I may tell you what was the result of the investigations from 1930 to 1940 about the machines. The very important outcome during that period was that a very, very small fraction of the problems which human beings will encounter can be solved with a machine or a computer system. That is, not all type of problems which we will encounter can be solved with the help of a computer. This was a very important fact which was discovered during 1930 or 40, between 1930 and 40. And it was not only said that it is only in terms of the existing computers. No, it was said that whatsoever may be the shape of the computer at any time in future, it will not be able to solve all problems which the human beings will encounter. Rather, they said, not only all problems cannot be solved, rather a very, very small fraction of the problems which human beings will encounter is capable or is amenable to solutions by a computer system. Second very important factor which was discovered by the theory of computer science, whose major developments took place during 1930 and 1940 was further. Out of the problems which may be on paper or in theory may be solvable with the help of a computer, only a very small fraction of those problems will be solvable within reasonable amount of time. That is, not all problems. First of all, it was said very small fraction of the problems which human beings will encounter will be solvable with the help of a computer. Secondly, out of those problems which may be theoretically solvable with the help of computer, a very small fraction will be solved with the help of a computer in reasonable amount of time. The second class, that is the set of all those problems which can be solved in reasonable amount of time, are called feasible problems. So, it was found the set of feasible problems out of the total number of problems which human beings encounter is very, very small. So friends, these are two types of things. These were one of the negative type of results what computers cannot do. The second type of developments or results which came out during this period were of constructive nature. That was, what is meant by solution of a problem, whether by the human beings or by a computer system. This was formalized. This was given a definition in terms of a formal system, whereas I have told you just now, a formal system is one which can be implemented on a machine, that is, which can function without the intervention of human beings. So, up till that time, the mathematicians had a vague idea what is meant by solution to a given problem. But nowhere it was told, there was no precise definition to which all mathematicians can agree, not only for the time being but for all the times to come in future, that what we mean by solution of a problem. Now this was precisely defined again during the period of 1930 and 1940. And friends, it is really a very significant contribution to the development of computer science in later years. And the definitions were not in one form but in a number of forms, which we will discuss later on. So these developments which formalize the notion of solution or proof of a problem was done during 1930 and 1940, and the point to be emphasized is that before this period the notion of solution or proof was just a vague, intuitive notion which was precisely defined during this period. So friends, before I go further into the details of the discussion of today's talk, I summarize that the theory of computer science is concerned about two major types of things. Number one, about the negative results. Negative results tell us that what a computer cannot do, whatsoever may be the power of the computer system at any time. And number two, what a computer does will be accepted as a solution to a particular problem. Generally what happens? For each problem, our intuitive understanding tells us whatever is claimed to be a proof is actually a proof or not. Whatever is claimed to be a solution is a solution or not. However, when we have very complex problems, our intuition may also not help us with whatever is claimed to be a solution. So this period between 1930 and 1940 gave us a test, a definition, that if these conditions are satisfied, then whatever is claimed to be a solution or a proof is actually a solution or a proof or not. So this summarizes the essence of theory of computer science, and whatever I have just said, you can see the significance of this. Because until unless the definitions were given during this period, how we could have said that the computer has actually solved a problem or not? Because if there are no definition, what we are to apply, what test or measure we have to apply in order to see whether the claimed solution is a solution or not. So this is not a very small contribution, though in everyday life while developing software this fact may not be used, but it is at the foundations of all the solutions which are claimed to be solutions. So friends, with this now I'll go to the further developments here. One of the things I told you, that whenever we study a discipline, to a scientist, whys, hows and whats arise. That is the difference between scientific attitude and the normal everyday life common sense attitude. Being computer science students in BCA or MCA, we must know what is the significance, a part of which I have already explained, but I like to go a little bit further, and I like to tell you that every theory, not only theory of computer science, but it is any theory, why it is developed, what is its significance vis-a-vis the discipline which is being studied, and then I will come to specially to the discipline of computer science. So friends, for this purpose, first of all, I like to tell you that what are the fundamentals of nature? What are the fundamentals of nature? The fundamentals of nature are matter, energy, change or evolution, and last but not least, which is rather may appear to be controversial, information processing. Again I repeat, in order to discuss the subject at the most fundamental level, I first of all enumerate what are the fundamentals of nature. Nature's fundamentals are matter, energy, change or information, information processing. Now, how do you claim that the information processing is also a natural phenomenon? Most of the times when people are told, they are rather taken aback. They think that, oh, information processing is just a human creation, it cannot be natural. But it is natural in the sense, I tell you, that for example, the earth goes round the sun in fixed amount of time almost. Year after year at a particular point of time we have the same length of the days and nights and so on and so forth. How it is happening? Until unless there is some information processing, how after the gap of 365 point some days the same things are repeating, there must be something. This is just even when a seed is sown, same type of tree grows up, same type of fruits are given by the tree. Until unless information processing is going from the seed to the tree to the fruits, it cannot happen. If a different seed is sown, then different type of tree, different type of fruits come. However, the seeds of the similar type are sown, then similar type of trees and similar type of fruits come. Why it happens? It happens because in the seed there is information and information processing. The genetic code is there, and there is a mechanism which is provided by along with the environment to decode whatever is the information there in the seed. And according to the environmental condition, the seed develops into tree or fruit, etc. So friends, information processing is also something natural which is obtained, which is ingrained in human beings from the general natural phenomena instead of being just a human phenomenon. So, now matter evolved in infinitely many forms And similarly, the energy also evolved in many forms like electrical, optical, solar, etc. Similar information processing also was only a natural phenomena, and gradually it has become man-mediated activity. As in the case of matter, earlier the matter was only natural, but gradually man started manufacturing things, and material things were obtained or being obtained and will continue to be obtained through the man-mediated efforts. That is, now the new materials are not just because of the natural evolution. Similarly, there were various energy forms, electrical energy, then there are other forms of energy, etc. However, later on, the man-mediated methods of creating or rather generating energy were there. So similarly, in the case of information processing, earlier there was only natural information processing. However, by and by, as in the case of matter, as in the case of energy, man-mediated processes of information processing also started coming up, and computer is now so well known that people have started thinking as if information processing is only human activity. But no, like matter, like energy, information processing is also a natural phenomena, and now it is being generated through man-mediated efforts also. So why computer science? As I told you in the beginning itself, that the computer science is the science of information processing. What a science does? A science actually gives alternative theories through finite number of words, so that the infinity of a phenomena is explained through the finiteness of the theory. So there are various theories, material theories are there, energy theories are also there. So similarly, there are a number of theories which were developed in the 1930 and 1940. What is the significance? Though I have told you, again I emphasize that the significance of a theory is to give the essence of an infinite phenomena. By infinite phenomena means a phenomena which occurs in nature almost throughout, in infinitely many places, in infinitely many forms, and if we start enumerating each of these, it becomes impossible for us to capture the essential idea behind a phenomena. So what the theories do? The theories, which are a finite number of basic principles or statements, tell us, give a view of the whole of infinity of a phenomena through finite number of statements or principles. So here, theory of computer science also does something like this, that the information processing instances are occurring all over the nature. What is the essential commonality in all those phenomena? That is given by theory of computer science. So friends, I hope you have understood the basic idea that why a theory is required. In essence, please look at the slide. The slide says that the computing or computation is the man-mediated harnessed information processing. As I just now said, information processing is a natural phenomena to begin with. Later on, we developed computer systems and other machines, and now we solve problems with the help of machine by storing finitely many facts, applying finitely many operations in a premeditated way. That is thought of as computation or computer science or computing. Okay. Computing is a complex phenomenon. Friends, as I told, there are infinitely many motions. On one hand, there is the motion of electrons in an atom at a very microscopic level. On the other hand, even the galaxies are moving around in the space. So the motions are infinitely many, ranging from the very small to the very large, moving at different speeds in different environments and all that. However, few laws of physics, earlier the Newtonian laws, then Einsteinian laws and other laws came which capture the essence of this. Similarly, in theory of computer science also, which is the phenomena of working on information, not working on the material, rather on the representations of the materials involved in a problem which is to be solved. We don't work on the material or the items of the problems, rather we work on the representations of the items involved in a problem, and then we manipulate according to some fixed, prefixed operations, and ultimately we come to something which we claim as a representation of the things which should be manipulated in a way to get the solution. So what is the distinguishing feature in the practice of computers? Computers ultimately are used as tools for solving problems, but the tools were earlier also there. But the earlier tools worked directly on the materials or items which were involved in a problem. The difference in the new situation is that now we don't work directly on the items which are involved in a problem, rather we work on their representations. This fact must be understood. So computer science is apart from the rest of the disciplines like chemistry or physics, that here we don't work directly on the items involved, rather we work on their representations. Now, as I said, we have a number of theories about the materials and motions. Similarly, it is the perspective by which, when we are discussing the atomic electronic motions in atoms, and when we are discussing the normal motion of vehicles on Earth, there are different theories, because a single theory may not be comprehensive enough to cover the motion of an electron within an atom and the motion of the vehicles on Earth and the motion of galaxies around each other or something like that. So it is the view or the perspective by which the various originators, the pioneers in the discipline, looked at the phenomena and they came up with a theory. In computer science also, as I mentioned, during 1930 and 1940, a number of pioneers were there like Gödel, Church, Turing, etc., who investigated, who analyzed the phenomena of computation from different angles, and they came with different theories of computer science. Before I go ahead, as I mentioned, it is computer science in one way also can be said to be study of algorithms. Algorithms, the definition of algorithm is the essence of a major part of theory of computer science, how the leaders looked at the solution or the algorithm in a formal way is the differentiating factor, but it was proved later on that all these approaches to looking at the solution or the algorithm are equivalent in the sense that any solution under one approach will lead to an equivalent solution to another approach. So friends, with this introduction, I may enumerate a few approaches which were generated during the enthusiastic work of theoretical computer scientists during 1930 and 1940. Please look at the slides. Number one, the approaches. Please look at the slide. I am enumerating the various approaches to the computer science. Please look at the slide. The slide says that one of the approaches is machine or finite automata approach, the culmination of which was through the efforts of Turing in 1936 when he suggested the Turing machine. Then there is another approach here, basically in the machine approach. What happens? that we think there is an instrument which can store a finite number of distinct symbols and sequences of these symbols and have some operations which work on these symbols, and just with these capabilities, if we are able to give the initial conditions in terms of these symbols and we operate those operations which are built in the machine, then ultimately if there is a solution, then that solution can be expressed in terms of the finite number of symbols and finite number of operations on these symbols. This is the essence of the machine approach or automata approach. Then the second approach to defining what is meant by a formal solution is the recursive function approach. This approach is apparently very simple in the sense that you assume the existence of few very elementary functions. For example, there is a function which maps every element to 0. This is a very elementary function which can be implemented on any machine. Then there are some other successor function is there. That is, for each natural number we can find out its successor. For example, if to this function 5 is given, it should return 6. If 25 is given, it should return 26, and so on. And the third is the projections functions, a set of functions. If there is an n tuple, then you can find out the ith component of that n tuple. So in this way you will have n different functions which map to the ith component, where I varies from 1 to n. If these functions are assumed to be implemented by any machine, then the most complex function which any machine can compute can be obtained by applying a number of composing rules. One of the composing rule is composition of functions, and some other rules. You can get the most complicated functions. This is the second approach to defining what is meant by solution or algorithm. So third approach, please continue, is the formal grammar or language approaches. And fourth is lambda calculus or functional programming approach. We'll discuss these approaches sometimes later on. Besides this, these four approaches actually gave us the definition of a formal solution, which we sometimes call algorithm. But in addition to that, the theory of computer science also handles some other topics. For that, please look at the slides again. The slides say, in addition to that, the topics which are part of theoretical computer science are computational complexity and unsolvable problems. What is the genesis of these topics? Friends, computational complexity means that of course you are able to give a sequence of steps by which the representation of the initial conditions of a problem are manipulated to reach a representation of the final situation, which may be called a solution. Now, there may be different routes of reaching from the initial state to the final state, or the solution state, if you like to call. Now, which one to take? If there are more than one solution sequence of solution steps, naturally we will like the one which takes lesser number of steps. So the complexity, computational complexity issue is something on this type, that out of the algorithms which we have available to solve a particular problem, which one is better than the other, where the definition of better is given in a formal way. This constitutes a major part of theoretical computer science, how to find out the time or space or other resources required to solve, to execute a particular solution, and that comparing the various solutions, if there are more than one solution, this forms one part of the theory of computer science. The other is unsolvable. Now friends, this is also very important subject, in the sense When initially we are given a problem, we may not be able to tell, and most of the times we cannot tell whether the problem is actually solvable with the help of computer or not. Why this question arises? I have told you in the very beginning that from the research of 1930 and between 1930 and 1940, it came out that a very small fraction of the problems which we will encounter will be solvable with the help of computer. So, when we encounter a problem, we are not sure whether it can be solved with the help of a computer or not. Because if it is not solvable by a computer system, then we have to adopt other means of attempting to solve it. So once this topic also is under the subject of theoretical computer science, how to know a particular problem can actually be solved with the help of a computer or not. So most of the problems which are unsolvable, for them there is another theory that how from one unsolvable problem we can find a set of unsolvable problems, that is the unsolvability of a large number of other problems can be settled by knowing that a given problem as unsolvable. So this is also a part of the whatever is the subject matter of theoretical computer science. So friends, as I mentioned earlier, Turing thesis also plays a very important role in theoretical computer science, in the sense, as I mentioned earlier, there are a number of approaches to finding out what is meant by a solution, how we should know that all these approaches are leading to the same definition. It is a thesis. Charles Turing, after a lot of investigation, propounded the thesis that all approaches must be equivalent. Anyway, with these remarks, friends, I may tell that in the rest of the next lectures, sometimes when we get some time, the opportunity of delivering lectures on theory of computer science, we will be discussing the machine approach, we will be discussing the primitive recursive functions approach, we will be discussing other approaches also. But just to have an idea what is the machine approach, you can have look at the figure. It is a map of sort of Turing machine, which has an infinite tape, which is semi-infinite in the sense that one direction on one end we can take a fixed end. For example, the symbol D is written on the leftmost corner. However, the right there is no end. Then there is some mechanism built in which can sense a particular symbol. That is, this tape is divided into number of cells. Each cell is capable of storing one symbol, and this triangle is a sort of sensor which can sense the symbol of the cell under consideration, and it sends to the control unit, which after sensing what is the cell under consideration, what is the state of the machine, can decide the next action. So this is the essence of what is the Turing machine is there. Apparently it is a very simple machine. However, it can do whatever the most complex computer system can do. So friends, with these words, I am just once again summarizing that the purpose of theory of computation is twofold. One is that not all problems can be solved with the help of computers. We must know only a small fraction of the problems which we encounter can be solved with the help of a computer. And secondly, formalizing the notion of solution with the help of a machine. I hope you have understood the essence of the subject, and with this we come to the end of this lecture. Next time we will discuss the other approaches. Thank you very much.